All right, everyone. So what I've done is this is actually the full answer key to the Unit 2 review for TCM. And what I'm going to do is just kind of walk you through and talk. You can pause this video and write down what you need at any time. And here we go. So a lot of this unit was about statistics and displays of data. So what we have here for question 1 is what's called a stem leaf plot. So when you make a stem leaf plot, you put the tens digit or the first number on the left column, and then the ones digits are on the right column. So as you can see here, I'll highlight it in green. That doesn't mean that people have 2, 4, and 9 as their data. What that means is that this information is fuel economy or miles per gallon that various cars get, and 12 miles per gallon, you write the 1 on the left and the 2 on the right. 14, you don't have to write another 1. You would just write a 4 on the right-hand side, and same goes for 9 for 19. And then we go to the 20s. So everything in the 20s here that's underlined now in pink and green starts with 2. And then, again, this represents 21, 22, 23, and so on. So stem leaf plot, that's how you would make one. That's how you would interpret one if you were given one and asked what was going on. Now, we also learned how to make what's called a histogram, which is sort of like a grouped bar graph, and we'll get to that in a second. But that involves, in this case, different data. And before we get to it, they ask you a couple questions. So what we have here, this is the heights of players in inches on a basketball team. And we have some in the 60s, some in the 70s, and one in the 80s. Now, again, what does that mean? Well, first of all, to give you some perspective, 72 inches is 6 feet tall. So, in case you were wondering just how tall these people are. But regardless, you don't have to know that. It just asks you for the mean and the median and the range to start with. Mean is the average. And the sum of all of these I already did for you. So normally when it's the average, you add all of them and divide by however many there are to save you some time. The sum of all these heights is 1,077, and there were 15 players. So dividing those gives us an answer of 71.8 inches. That is the average right there. The median, or the middle point, is always, they have to be in order from least to greatest, which this data is. You can see that here. And this is what we sometimes refer to as the crossout method, meaning 67 is the smallest, 80 is the biggest. If we keep crossing them off little by little, eventually we will converge on the median. Now, two things can happen. One, you can be left with one number. That's the median right there. If there's an odd number of terms. If there had been an even number of terms, let's say we were down to these two, all right, then you would find the point that's halfway between those, and that would be your median. But in this case, we had an odd number of points, so we were able to just narrow it down to a single value, that being 72. Range, if you're ever asked to find the range, that's just max minus min, biggest minus smallest, and the range of heights is 13 inches. Now on to histogram. So what I meant by a grouped bar graph, I said that just a second ago. A histogram, instead of making a bar graph and having a bar at 67, a bar at a height of 2 for 68, a bar at a height of 3 for 70, that can get redundant. What a histogram does is it groups them together. So what this information means is starting at 65 and counting by 5, that's what scale means, end at 85. So that's what we did here. That's what you see in gray. And in between these numbers, 65 and 70, you're going to count how many players were between those two data points. So if I go up here, how many were between 65 and 70 are those three. That's why they were boxed in green to begin with, and that's why that bar goes up to a height of 3 right here. Now, if you're thinking to yourself, why didn't I include 70? If you remember, when you do a histogram, when you land on a tick mark, 70 for instance, that is always part of the group to the right. So 70 right here, that's part of this group. All right, so inside this bar here, this was 60, what was it, 67? Let me double check. 67, 68, and 68. That's who actually was in this group here. That's why it's only 3. In this next one, the reason it goes up to 9 is because everyone from 70 to 74 is going to go in this bar. Because if anyone's 75 inches tall, they're part of the group to the right. So what that means, all of these numbers here, that's what is in that bar that has a height of 9. So 70, 70, and 70, they're all in that group. So our 71, all of those 72s, and 74. That's why there's 9 things. 75, as you can see right here, well, that's part of the next group because that would move to the right. It's always to the right of the tick mark. And then same with 80, it would move to the right. And that's where we get the heights of that histogram. So whenever you're given a set of data, if you have a particular number that lands on a tick mark, like 70, it has to be included on the group to the right. Or in this case, 75 had to be on the right, as did 80. So those are the correct heights of that histogram. All right, and over here there's a little description of what I just said in green. All right, now another thing we talked about was what's called 5-number summary. Now, since we don't all have a calculator based on the situation at hand, I gave you the 5-number summary, and that is a quick snapshot of your data. So every 5-number summary, that's what this says right here, consists of the following things: the minimum, or the smallest point, the median, the middle point, the max, the largest point. And this is from the basketball player data above, so we already knew those 3 things. And then you have this thing called Q1 and Q3, which are 70 and 74. And again, what that represents, that's like saying the first quartile or like the 25th percentile, if that doesn't make sense. Basically, Q1 is the middle of the data from 67 to 72, and Q3, 74, that's the middle of the upper piece of data from 72 to 80. So what those numbers tell you, they help you create what's called a box plot and help you check for what are called outliers. Now, outliers are extreme points. So, if you have a team of high school players here, that's what we're assuming these are right here. This person here, 80, that would be someone who's actually 6'8". Now, there could be high school players that are 6'8", but maybe that's such a tall person compared to everyone else on the team, they're an outlier. Or similarly, maybe this person here, 67, that's someone who's only 5'7". That's not that unusual, but maybe compared to everyone else on the team, it's incredibly small. They might be an outlier. Now, you can't just guess who's an outlier. The only way you can check that is through a formula, and that formula is right here. So there's this thing called the interquartile range that is used in your formula right here. So basically, you have to find what are called fences. A fence is a cutoff value for outliers. So if you are lower than the lower fence, you're an outlier. And if you're greater than the upper fence, you're an outlier. So the formula for those is here. I will always give you that. And what you would do is plug into it. So this work you see right here, we plugged in Q1 minus 1.5 times Q3 minus Q1 and got a number 64. Now, the reason there is no lower outlier is because the shortest person on the team was 67 inches tall. If that number for the shortest person on the team was less than 64, it would have been an outlier. So what sometimes confuses people is they get this answer, 64, and they go, oh, it's smaller than 67. But that's not the idea. The idea is you're an outlier if 67, the smallest person, the minimum, is less than the lower fence. Well, the lower fence was 64. 67 is not less than 64. You don't have a lower outlier. Now the upper outlier needs an upper fence formula. That's what you see right here. That's Q3, or 74, plus 1.5 times Q3 minus Q1 again, and we get 80. Now, if you remember, 80 was the tallest person on the team. Now, technically, you normally don't land on the outlier. We're saying there's no upper outlier here. Usually what would happen is you'd have a number that's definitely greater than the fence. In this case, you landed on the upper fence. And the reason there's no upper outlier, 80 is technically not greater than 80. It's close. That person who's 6'8" is definitely near outlier status, but they aren't one. All right, so again, if that's a little confusing, take your time. Pause this video, look through it, check your formulas, check the work. But the long story short of it, if you're an outlier, you have to be lower than this lower fence formula or larger than this upper fence formula. And if that's a little confusing, this visual here, a box plot, is a visual of that. And a box plot is basically a graph of the 5-number summary. That's why it says draw the 5-number summary. So this was the min. This was Q1, the median, Q3, and the max. This information over here, this is just to draw the x-axis. That's not saying the minimum 65. It's saying you should draw from 65 to 85 counting by 5. And I kind of graphed this box plot above it. Now, if there was an outlier, you would have had a point like out here. It would have been so low, you would have marked it with a star. Or so big, you would have marked it with a star. And if you recall, the fences that you found, one of your fences was 64. So this might help make sense of this. Here's the lower fence. Do you have any data over here to the left of it? No. Your data's right here. So you don't have anything less than or to the left of this red mark. That's why there's no lower outliers. The upper fence was right on 80. But you don't have anything to the right of this red line. Nothing's over here on the right. So you don't have any upper outliers either. If you did, let's say someone was 85 inches tall on your team, well, they'd be an outlier because their data point would be outside of the red fences. So maybe that visual helps you understand that a little bit more. All right. And then something else we talked about in class, skewed left is a way of saying you have a low outlier. Skewed right means you have an upper outlier. If you don't have any outliers, you'd say your data is pretty much symmetric, which we did. And the only other thing on here before we get into the other part of the unit to review were z-scores. So z-scores were basically telling you how many standard deviations above or below average you are. And to summarize that for you, here's a formula. X would be your actual data. X with the bar over it is actually the average, which it says right here, the mean. And S stands for standard deviation. Those are things you'd be given in a problem. So for instance, what they're saying right here is voters in the U.S. election 2016, the average age was 50 with a standard deviation of 15. So what they're saying is if someone was 24 years old, were they above or below average, and by how much? Well, first of all, if 50 is the average, I think we can all agree a 24-year-old is less than average. They are below average. And what that means is you'll get a z-score that is negative. If they were above average, like if they were 90 years old, you'd have a positive z-score. And all a z-score tells you is if we're counting by 15s, that's our standard deviation, by how many standard deviations under 50 is 24. So you would plug into this formula right here, and you would get an answer of negative 1.7. Now, again, we're not doing a full-on stats review here, but what that basically means is a 24-year-old is nearly 2 standard deviations below average. And in part B, they're saying, let's say you have a z-score of 0.75. That's someone that is almost a full deviation above average. Since you're counting by 15s, that's your deviation. Someone who's almost 1 deviation above average is someone who's almost 15 years above 50, but not quite. And so what that would mean is you'd have to plug in for z on the left, x on the right, and cross multiply and solve that. and you would discover that a 61-year-old person would be about 0.75 standard deviation above average. Now, again, there's a lot more we could say about this, but what we basically learned in class was if that's confusing you, you can make what's called a normal model. So, a normal model, everyone, would be as follows. So let's say you're told the average age is actually 54 and the standard deviation is 20. What that means is you'd put the average smack dab in the middle and you would count by standard deviations. So I'm counting by 20 as I move to the right, or I'm subtracting 20 as I move to the left. So what a normal model does, what's cool is that in real life, things that follow a normal curve are easy to analyze. And you can use programs and algorithms regardless of if you're looking at voting age, if you're looking at SAT scores, if you're looking at 3-pointers made in a season. There's lots of things that follow a normal model, and you can analyze them in a calculator or with a program if you talk about them as z-scores. So that's kind of where that comes from. Again, a visual to describe what this up here was that was confusing. And the other thing we learned in class was that if you're one standard deviation left and right of the average, 68% of all of your data will land in there. So in other words, 68% of all U.S. voters in that election were between 34 and 74 years old. You then learned if you go 2 tick marks to the left and right, meaning you go all the way out to 14 and 94, 95% of voters in the election were between those 2 ages. And lastly, if you go 3 tick marks to the left and right, you discover that's where nearly all the data, 99.7% of data, is 3 tick marks left and right of 54. So there's one other part to the Unit 2 review. I'll make a video of that in just a second, but I hope that helped a little bit. And again, if you need to pause, go back, answer some questions little by little.